Hey everybody! Last week we focused on the first half of the conversion of pyruvate to acetyl-CoA. This week I would like to look at the second half of that reaction. You will have to bear with me because the mechanism is a bit new for us in some ways, but I felt like it was better for me to finish teaching this concept than to pick a more familiar yet unrelated mechanism. So this week we will be talking about dihydrolipoyl transacetylase, a mouthful, and its oxidative properties. Because we are going to add to what we learned last week, I would like to quickly review that process and a bit of the background information. So the reaction we are looking at comes between glycolysis and the citric acid cycle. It is the conversion of pyruvate, the product of glycolysis, to acetyl-CoA, the molecule that enters the citric acid cycle. And this process is mediated by pyruvate dehydrogenase, or the PDH complex. I'm not sure I mentioned it last week, but this takes place in the mitochondria. An important thing to remember is that this reaction is labeled an oxidative decarboxylation reaction. It has this name because a 3-carbon molecule is converted to a 2-carbon molecule, and a hydroxy group is oxidized to a carbonyl. Last week we talked about enzyme 1 in the PDH complex, also known as pyruvate dehydrogenase. In that first portion, PDH, with the help of a coenzyme called TPP, converted pyruvate to carbon dioxide, and we were left with hydroxyethyl-TPP, which you can see below. And you can see the reduced acetyl group that we were talking about. You may recognize this figure from last week. I just think it's a really great summary of the complex and everything that happens in it, as well as enzyme names. So this week we will get to the oxidative portion of the reaction, but in order for this to happen, we need a new enzyme, and that enzyme is dihydrolipoyl transacetylase. The most important part of this enzyme in this particular reaction is the lipoyl group. A lipoyl group looks a bit like a thioacetyl, which is something we have worked with, but a lipoyl has an important difference. The sulfur atoms are directly bound to each other, rather than being bound to the same carbon, and you can see that difference here. So this allows the lipoyl ring to break more easily, which will be necessary for the oxidation. It is much easier to break this sulfur-sulfur bond than it is to break either of these sulfur-carbon bonds. So the role of the lipoyl group and dihydrolipoyl transacetylase as a whole is to drive the oxidation of the hydroxy group. So now finally the mechanism. Oddly, this mechanism is drawn from right to left, so I've labeled the starting material and the product just to clarify what's going on. Like I mentioned earlier, we are starting with hydroxyethyl-TPP. Oops. And this sounds complicated, but we can actually see why it has that name pretty easily. So here we have 2 carbons, which we know is called an ethyl, and attached to the end of that is a hydroxy group. And then here is the TPP molecule, and these 2 groups are just connected by this bond, this double bond between them. So, like we saw in part 1 last week, the enamine portion, which is right here, acts as an enolate. The lone pair on the nitrogen drops down to form a double bond, causing the electrons from the double bond that's already there to act as a nucleophile and attack one of the sulfur atoms. When this happens, the sulfur-sulfur bond in the lipoyl breaks, and a hydrogen is grabbed from water to protonate what would have been a negative sulfur atom. And now we can move on to step 2, and TPP needs to leave. Thankfully, we now have water's conjugate base available to deprotonate our alcohol. So when the alcohol is deprotonated, the electrons from the OH bond drop down to form the carbonyl, causing the bond between TPP and our molecule here to break. Because carbon, we know, can't have 5 bonds, and TPP is the best leaving group. Like I mentioned last week, the positive charge on the nitrogen allows for the stabilization of the negative charge on this carbon, which is why it's the best leaving group in this case. So now that TPP has left, we can move on to step 3. And now we introduce a very important substrate, which is coenzyme A. We can leave this abbreviated because there's really no need for us to know what this rather complex molecule looks like. All we really need to know in this situation is that it contains a terminal thiol or SH group. A thiol has a pKa of about 11, while an alcohol has a pKa of about 16. If you remember from first semester, a low pKa value indicates that the compound is acidic and will easily give up its proton to a base. This means that a thiol can be relatively easily protonated by water, even more so than an alcohol actually, so that's why this substrate is able to react so easily in relatively neutral conditions. And we can see from its pKa that a deprotonated thiol group, or a thiolate, is a relatively weak base, but an excellent nucleophile. So here, they show that this group has already been deprotonated by water. Like we would expect for any nucleophile, the thiolate attacks the carbonyl, causing the electrons to kick up and form a negative charge on the oxygen. Finally, step 4. And now we need enzyme 2, the dihydrolipoyl transacetylase, to leave. And that's exactly what happens. So like we have seen over and over again, a lone pair on this negative oxygen drops down to form that carbonyl, and our leaving group, being the lipoyl, leaves. As this happens, water protonates the sulfur so as not to leave it with a negative charge, and we end up with our final product, acetyl-CoA. Another quick note, in step 3, which I won't cover, the added hydrogens are removed from the lipoyl group, returning it to its original cyclic form so that the reaction can be repeated. On this slide, I have included the entire arrow pushing mechanism, including this week and last week, just to give you a good overview of what we've looked at. So to review what we've learned, we looked at the reaction that takes place when pyruvate is converted into acetyl-CoA via an oxidative decarboxylation reaction. In part 1, which we looked at last week, we saw the decarboxylation portion with the CO2 leaving group. Then in part 2, which we looked at this week, we saw the oxidative portion as a hydroxyethyl group was oxidized to an acetyl group. In order for this to happen, we needed a lipoyl group and the substrate coenzyme A. The PDH complex regulates the entry of acetyl-CoA into the citric acid cycle, and it does so consistently. This is a very important enzymatic complex that allows cellular respiration to be carried out in a controlled manner, and this is vital to cellular life. Though as biologists, we are probably very familiar with cellular respiration, so I think we've learned it like 3 or 4 times now. I hope you enjoyed learning something new about one of the intermediate steps and looking at it through an organic lens. So I can't wait to see you all again, and I wish you the best as the year comes to a close. And yeah, thank you so much for listening.